Hello. So in this lecture we will be talking about heat transfer in the Taylor flow regime. So as we know that in microchannels the surface area to volume ratio, that is surface area density, is large when you compare with large diameter channels or conventional channels. So what happens that one can get large surface area for heat transfer or large interfacial area for heat transfer, and that results in enhanced heat transfer performance in microchannels. Additionally, the diffusion length, because in a channel when the flow is happening during the convective heat transfer, the radial conduction happens from the channel center to the wall. So that is the diffusion length, or that is the conduction length, and as the channel size becomes smaller, this conduction length becomes smaller, so the heat transfer rate for the same conductivity will be increased. Now looking at some of the applications in which the heat transfer in microchannel is being used increasingly are, say, electronics cooling. So in electronics cooling, the cooling of different parts of computers or other hardwares, as we know from Moore's law that in about a year the number of chips on a motherboard or on a number of chips increases almost every year. So that increases the requirement for the cooling of the electronic equipment, that increases that the larger heat flux, when the number of chips are increasing, then the larger heat flux need to be removed. So at one stage the number of chips that can be put are limited by the heat flux that can be removed from the surface. So it is important to develop technologies which can enhance the heat transfer performance for electronics cooling, and one of those technologies is based on microchannels. So in that case, when we have a single phase flow, now the performance can be further increased if in place of gas cooling one uses liquid cooling, because the thermal mass of the liquid is more than that of gas. Further, if we want to increase the performance further, then additional means of heat transfer mixing is required, because in microchannels we always have flow to be laminar, or in most of the cases the flow is generally laminar. So there is no mixing offered by the turbulent nature of the flow. So people have devised different active and passive means of mixing, one of them being using the, say, serpentine channel, which causes the flow to have a secondary flow in the secondary direction. So if this is the cross section of the channel, then in addition to the flow in the streamline direction, there is another flow in the cross section of the channel at that, and that enhances the mixing in the channel. So these are called Dean vortices. So that can be one of the solutions. Another solution is where people use baffle in different arrangements to enhance the radial mixing by convective means, and so on and so forth. So further on, if we want to increase the further heat flux, or for a single phase flow, for liquid only flow, if the heat flux is increased at one point, it will start evaporating, and in that case we will have boiling in microchannels. So that becomes important. Or one can have another means of mixing, that the flow can be segmented which is generate a Taylor flow regime using bubbles or droplets. So, if one uses bubbles, then one is just segmenting the liquid flow and enhancing the internal recirculations, and the heat transfer increased significantly 2 to 3 times depending on the flow conditions. In comparison to gas liquid segmented flow or gas liquid Taylor flow, the heat transfer is further increased if one have liquid liquid flow, because now both the phases will have internal recirculations and both the phases will also increase or will contribute to the heat transfer. So, the heat transfer can be further increased when one compare with the gas liquid flow. Okay. Another application is exothermic gas liquid reactions. So, a number of applications which require or for which the microchannels are being used for are for the reactions which are highly exothermic, because it is relatively safer to carry out these reactions in microchannels. One of the reasons being that higher heat flux can be handled in small diameter channels. And additionally, when we have gas liquid reactions, the mass transfer is also enhanced by the by carrying out these reactions, because the interfacial area has increased significantly when we compare with normal channels or conventional channels. Then they have applications as compact heat exchangers in aerospace engineering applications. As we can guess that the design of aerospace equipment is limited by that one should have the highest performance with the minimum mass, so that more and more payload for space applications or more and more load in the aeronautical applications can be taken there. So, one would like to have the lowest mass possible, and that will be achieved, that can be achieved by having high interfacial or high surface area density. So, it is being explored for application in aerospace engineering. Then offshore petroleum engineering, where again one would like to have compact heat exchangers. So, the offshore industry is using the compact heat exchangers. One of the companies that supply the heat exchangers is named as Heatrick, and it is a part of a company called Maggot PLC. So, you can look at some of the applications of these compact heat exchangers. The heat exchangers that Heatrick offer are known as PCHE or printed circuit heat exchangers. Okay. So, printed circuit heat exchangers, what they are, that that is one of the way to scale up the microchannels for industrial applications. So, in a metallic plate, a number of channels are etched which are of the millimeter size or smaller dimensions, and then another plate which has the same kind of channel, a diffusion bonded on this plate, and then these plates are stacked together. They may be thousands of channels in a plate, and thousands of plates or hundreds of these plates can be stacked together, and then the flow happens in these. Now, one of the challenges in such cases will be the distribution of the fluids in the manifold, but that is not our topic of discussion today. So, these printed circuit heat exchangers are already being used for a number of applications say for example offshore applications by different companies. Okay. So, coming to heat transfer in Taylor flow regime, generally it is when we are looking at it, it is convective heat transfer, that is because the flow is happening and the heat is either entering in the channel and being removed by the fluid, or it can be the other way around, that heat is being taken away in case of say exothermic reactions. They can offer better heat transfers than liquid only flow, as I just said, because the typical structure in a Taylor flow is we have the dispersed phase, these may be bubbles or droplets, and in between these bubbles there is internal recirculations in the liquid slugs. So, this internal recirculation causes that the hot fluid from the wall that comes towards the center and the efficient mixing happens. So, it enhances the heat transfer with respect to the liquid only flow, of course subject to the condition that if these dispersed phase is bubble and then the volume of bubble should be smaller, so that the efficient heat transfer is happening. Now, because in gas liquid flow they do not contribute to the heat transfer, and as I said earlier that this heat flux that can be removed can be further increased by phase change, where one get the QL or the latent heat that can be removed. So, one can remove further heat flux or higher heat flux by evaporation and boiling. Okay. So, let us look at some of the basics, because this course is not about heat transfer. So, let us remind ourselves some of the basics of convective heat transfer. So, when we talk about forced convection, it is often represented by a non-dimensional number which is known as Nusselt number, and it is abbreviated as Nu and given as H d over k, where H is heat transfer coefficient, d can be taken as channel diameter, or in case of non-circular cross sections, one can take this as hydraulic diameter, and K is conductivity of the fluid. Now, in case of two phase fluids, it is important to understand which phase of conductivity should be used in this expression, because this is a comparison of if you can rearrange this H over K over D. So, the convective heat transfer divided by the conductive heat transfer in the radial direction. So, the conductivity of the phase in contact with the wall, that is what should be used. Now, so we know what D is, the diameter of the channel, and what K is, the conductivity of the fluid, which is the property of the fluid, and we can find it out, or we can calculate by using different formula available in transport phenomena. Now, H is the heat transfer coefficient, which is defined as Q wall over area of the wall. It is important to remember that this is not the cross sectional area, but the area of the channel. So, for a cylindrical channel it will be 2 pi r l Q w over A w into T wall minus T bulk or T bulk mean. So, T bulk or T mean. So, generally there can be different kind of boundary conditions one can have on the wall. So, in general one encounter the constant wall heat flux or constant H boundary condition, which is called, or it is constant wall heat flux. So, it is called H boundary condition, that the heat flux is constant. The another boundary condition is constant wall temperature. So, in this case it is called T boundary condition, or the third boundary condition is mixed boundary condition, where one will have a relationship between Q wall is equal to H A, say T wall minus T. And so, in this case if H is known, then this can be used as a mixed boundary condition. One can see that Q wall from Fourier's law of heat transfer is equal to K dt over dr at the wall. So, this is basically the boundary condition in which the gradient of the temperature is being defined. Okay. Now, the question comes, when we are defining the heat transfer coefficient, T wall is wall temperature, and this T, which is bulk temperature or mean temperature, what this temperature is. Because if we look at the flow in a channel, if there is heat entering at the channel wall, the temperature profile may look something like this, which suggests that the temperature will be highest near the wall, and then it will be varying and become minimum at the center, and then again increase towards the wall. So, clearly the temperature varies according to the with the radius of the channel. So, which temperature should we take? So, in this case the mean temperature is defined as is equal to T mean or T bulk. Mean is equal to integral rho u C p T dA divided by integral rho u C p dA. So, where rho is the density of the fluid, u is the local velocity of the fluid, Cp is the heat capacity, and T is the local temperature of the fluid, and dA is the area of the cross section. It has to be integrated over the area. It has to be integrated over the area. So, what you can observe from this, that the only difference between the integrals at the top and bottom is T. So, this is basically mass weighted average of the fluid. Okay. So, that is bulk mean temperature. Now, because this is flow in a channel, so we will remind ourselves the temperature profiles for two often used boundary conditions, for H boundary condition and for T boundary condition. So, in a constant wall heat flux case, as one can see or one can speculate that the temperature of the wall will be increasing and the temperature of the fluid will be increasing. We have this in the fully developed region on the when we say fully developed region, this is thermally fully developed region. So, in the thermally fully developed region, we will a little later we will talk about how do we define the thermally fully developed region in a channel. So, this is the upper line is for T wall and the line below is T bulk, and we can see that they are parallel to each other and the slope of these lines can be found by writing the heat balance equations. So, the temperature of the wall and temperature of the fluid both increases linearly and the difference between them is constant everywhere for the fully developed flow case. Now, for a constant wall heat flux case, this will not be the case, but what we will have is the temperature and x. So, the temperature of the wall will be a constant because that is what the boundary condition is, and then as the fluid start flowing into it, the temperature of the fluid will increase and then approach towards the temperature of the wall, and that will be achieved only at infinity. So, in this case we can see the difference between the temperatures keep decreasing as we move in the axial direction, and Q is equal to K dt over dr at the wall Q wall. So, we can see that the Q wall in this case will keep decreasing almost exponentially this case. So, these are the typical temperature and heat wall heat flux profiles for single phase flow in a channel. Now, for thermally fully developed flow, so if we remember or if we remind ourselves that hydrodynamic fully developed flow refers to that dV x or the velocity in the axial direction, or let us say dVz over dz is equal to 0. So, the velocity profile is not changing along the axial direction. So, if we look at the velocities at two different locations x1 and x2 in the channel, x1 and x2, then we will find that the velocity at the corresponding radial locations are same in both the cases. Whereas, if we look at the temperature profiles here, that clearly tells us the temperature has to increase because it absorbs more and more heat. So, we cannot have that the thermally fully developed flow in analogy with the hydrodynamically fully developed flow, we cannot have dt over dz is equal to 0. That is not possible for thermally fully developed flow. Whereas a non-dimensional temperature, so the temperature do increase, but the non-dimensional temperature, which can be defined as T wall minus T divided by T wall minus T mean, and d theta over dz is equal to 0 for thermally fully developed flow. Okay. So, let us remember all this. Now, what we talked about, that when the flow is has developed, what are the temperature profiles and how we define the non-dimensional temperature and so on and so forth. So, it can also be seen shown that for laminar fully developed flow, the Nusselt number in a channel for fully developed flow and fully developed heat transfer, the Nusselt number is a constant. So, for H boundary condition, NuH is equal to 4.36, and for constant temperature boundary condition, it is about 3.6, around that. Okay. So, for developing flow, as one can expect that the heat transfer or the heat transfer coefficient or the Nusselt number will be higher when the flow is developing, and then eventually it becomes constant. It has been plotted, the Nusselt number, the local Nusselt number NuX, it has been plotted along the channel length. When I say local Nusselt number, that means it is being calculated along the length of the channel. So, NuX is H d over k, and H is QW x, because this is constant, and T wall at the x location minus T bulk at the x location. It does not consider the entire this thing, the heat transfer from the inlet to this point. This has been plotted, only the heat transfer at the cross section. So, that is why it has been termed as NuX. So, the heat transfer coefficient keep decreasing as we move in the axial direction. Notice the non-dimensional parameters at the x axis. What we have here is x over d r e p r. So, all of you will know that p r is defined as C p mu over k. Now, we can rearrange this as mu over rho divided by k over rho C p. So, mu over rho is known as dynamic viscosity or momentum diffusivity, and k upon rho C p is known as thermal diffusivity. So, this is basically the ratio of momentum diffusivity and thermal diffusivity. The Prandtl number is the ratio of momentum diffusivity and the thermal diffusivity. So, one gets this the non-dimensional number that is important in this case is x over r e p r, and this Prandtl number is a function of the property of the fluid only, and this decreases. There are different correlations that has been given, and one of them is that the Nusselt number decreases as x over d REPR of this non-dimensional number is to the power minus 1 by 3 when this is less than 0.03, and then it decreases according to this equation when x by d REPR is greater than 0.03, and this number inversely this is written as, we can change this to small d for uniformity. So, the Nusselt number is written as d over x REPR. So, this number or this term is also known as inverse Nusselt gave an analytical solution for a hydrodynamically fully developed and thermally developing flow, and it is a series solution. So, to simplify the solution, a number of approximation has been presented, and this is one of those. So, what I would like to emphasize here, that the developing Nusselt number is a function of inverse Nusselt number or Nusselt number, okay, which we will use later on when we develop the model for Taylor flow heat transfer. So, coming to heat transfer in the Taylor flow regime, the flow in Taylor flow regime is pulsatile. So, the flow changes with time, but it is periodic. So, it repeats itself after a certain time, or you can see this periodicity in space as well. So, if you are standing at one place, you will see one bubble coming along, and then one slug comes in, and then you have another bubble coming along, and this will be periodic. So, you can see if you are staying at one place, and you can see the volume fraction varying with respect to time, and this variation will be periodic. Similarly, if you are looking at in space, so at one time instant, if you look at, you will have number of bubbles at different at regular intervals. The distance between the two bubbles will be same, and the shape of the two bubbles will be same. So, the flow is periodic in space as well. Okay. Now, to do experiments for this for Taylor flow, one need to make sure what boundary condition is being used, and one also need to look at that what kind of heat transfer one is looking at, developing or simultaneously developing hydrodynamics and heat transfer, or they are looking at the heat transfer or the hydrodynamics of the flow has already developed, and the heat transfer is developing, and then it becomes fully developed. Now, when we do simulations or when we are studying, we can decouple phase change easily. We can say that we are not going to include a phase change model in our computational model, say in CFD, but when this happens experimentally, then there is no way to suppress or it is difficult to suppress the heat the phase change that might happen because of evaporation. So, what one can do, that it can be minimized to the maximum extent possible, and that can be done if one uses a non-volatile gas liquid combinations or non-volatile liquid, and the temperature of the fluids is at slightly lower range. So, the volatility or the evaporation rate is negligible or small, very small. Now, so then the question comes, when we measure, what is to be measured? So, it is Nu is equal to H d over K. So, if one have specified a constant wall heat flux, which is generally the case during the experiments, then what is need to be measured is T wall and T bulk. So, the T wall can be easily measured by putting the thermocouples at different locations on the wall. or by different wall temperature measurement techniques. However, it is not easy to measure bulk fluid temperature, because if one put a thermocouple inside the channel, then the flow behavior is going to change because of the presence of the a sensor, a temperature sensor, or that is put there. Then in most of the cases, the temperature in the channel wall. So, if let us say this is the channel, this is the internal wall of the channel, and this is the outer wall of the channel, and this is the channel edge thickness of the channel. So, this is Ri and this is Ro. Now, the sensors will be put somewhere here, or the wall temperature will be measured. So, one need to take into account the heat transfer that is happening from here to the liquid solid interface. So, in general, when one put the temperature sensors here, then one can obtain an analytical solution for the conductive heat transfer in this direction, or if one want to take into account the axial heat transfer also, then one can have full 3D simulations to look at the effect of conjugate heat transfer. Okay. So, all these factors needs to be thought about when performing the experiments. So, this is a typical experimental setup in which the liquid is coming from a liquid tank, and the nitrogen gas is being supplied, and then the inlet fluid temperature is being measured. Then they come into a mixing section, and the fluid move along the test section, and the wall temperature is being measured at different sections. The wall is being heated by a power supply. So, this is a test section that was used by Ms. Leong in her experiments at the University of Sydney, and then the outlet temperature is measured. They have also arrangement for looking at the and confirming the flow regime in the channel, and then it is being brought together, being brought to outside and released in the atmosphere. So, that is a typical experimental setup, and what is being measured, they have a H boundary condition in this case, and the wall temperature is being measured at different sections. Okay. One is advised to further look into the details of the test section, because this is there is lot of detail in while designing the test section, especially the H boundary condition or T boundary condition in these blocks. Okay. So, the another test section that has been used by Walsh et al. It is a similar test section, and they have made sure here, actually they have also made sure that the flow is hydrodynamically fully developed, and then there is heat being applied on it, and this heat is being applied by Joule heating, and the local measurement of surface wall temperature is being done, and using an IR camera probably, and then this is different tube cross sections they have taken, and wall thickness and the length of the heat section. So, then they are also looking at the fluid behavior, the flow regimes at the exit. Okay. So, while looking at the Taylor flow behavior, now we have two phases, gas and liquid or liquid phase. So, one need to define a Nusselt number, or one need to revisit the definition of Nusselt numbers. So, we can define a local Nusselt number, Nu is equal to H d over K, and because it is always the continuous phase which is in contact with the wall, So, K can be K of the continuous phase, H is the heat transfer coefficient and D is the diameter of the channel. Now, H is defined as Q wall over T wall minus T bulk. So, we will be defining these definitions for H boundary condition. Most of the discussion that we will have in this lecture will be based around the constant wall heat flux boundary condition. So, this Q wall is available from experiment. As it is an input. T wall is measured. Now, generally T bulk is a problem. Okay. So, what we are looking at here is the local definition of Nusselt number. So, NUX, everything else is going to be same at everywhere, all the cross sections. Q wall and the temperature of the wall is at that particular location. Now, we also need to define T bulk X. So, T bulk, we remember the definition of bulk temperature, then it can be defined integral at the area rho u x if the area or if the axial direction is x, and rho u x C p t at the particular location d a divided by integral over the area rho u x C p d a. Now, because there can be a backflow in the liquid. So, if we do not take into account only the magnitude of the axial velocity, then the terms will cancel out and we will have a wrong definition or sometimes a very small bulk temperature which does not represent the bulk temperature correctly. So, we have put that the absolute value of the axial velocity is being taken into account here. So, that is our local bulk fluid temperature. However, this is good if you want to do computations and we can get the local Nusselt numbers at different locations in the channel. But if we want to compare this with the experimental data, we do not have, we might have with the techniques available now, we can get the wall temperature locally, but it will not be possible to get the bulk temperature with the same definition. So, this is generally not used for the design calculations. Now, so for design calculations, we also need to have a overall Nusselt number. Now, because Taylor flow is periodic, so if we consider the flow when the heat transfer also have become periodic, then we can analyze flow in one unit cell which consists of one bubble or droplet and the slug around it. And once we have obtained this, we can use the same Nusselt number for the entire channel. So, it is easier to understand the behavior in one unit cell which consists of one bubble or droplet which is the dispersed phase and two halves of the liquid slug on the two sides of the unit cell. Okay. So, when we define the Nusselt number for a unit cell, we need to see Nu unit cell is equal to H d over K. K will be K liquid, no change there. D will be the channel diameter. H is equal to Q wall over T wall minus T bulk. So, now remember this is for the entire unit cell, which consists of the bubble or droplet and 2 halves of the liquid sludge. So, the thermal conductivity, as we discussed already, that it is always the continuous phase or the liquid phase which is in contact with the wall. So, the conductivity of the continuous phase will be taken into account. The wall heat flux, if we have the any boundary condition which is not constant wall heat flux, then we can get area average, area weighted average of the heat flux. And the wall temperature, that will be measured, and for calculations if we want to get the, because here what we want is the area weighted average. So, or the wall temperature in the entire location. So, we can do it integral area of the wall T wall dA divided by integral area of the wall dA. So, remember this is for a circular channel, it will be integral x location to x plus L, which let us say this is LUC, and this is T wall 2 pi r dx divided by integral x to x plus LUC T wall 2 pi r dx, not T wall, this will have only 2 pi r dx. So, 2 pi will cancel out and we can get the area weighted average. Now, the bulk mean temperature T bulk will have the same definition, but now the integral will be over the entire unit cell. So, we will have integral UC. Remember that in this case also we have two phases. So, we will have the gas phase and the liquid phase, depending on at what location what phase is present. So, we will have integral rho u x Cp T dV divided by integral rho u x Cp dV. So, that will give us the bulk mean temperature. Now, one can see and confirm for himself that this bulk temperature will not be same if one sums up the temperature at different axial locations, or it will not be simply integral Tb x dx, say x to x plus x, that will not be the case. So, one need to be careful when defining this. Okay. Now, so in the experiment, the Nusselt number estimation is done based on the axial length. So, if this is the channel from where it is being heated, the channel wall is being heated, and the total heat flux to this is, let us say, Q in. So, we can write a heat balance at a location x from inlet. So, it can be written as m dot Cp, and m dot Cp is for two phase, and Tb x or bulk temperature at x location minus T inlet, where T inlet is the temperature at this location, is equal to Q in x by L. So, this is the heat flow rate, and if this the Q in is for the entire length L, then what we are taking, the how much heat has gone in this, that will be equal to the heat absorbed by the liquid or the gas liquid flow. So, that will be m dot Cp. M dot Cp will have to take into account that there are two phases present in it. So, Tbx minus T in, and of course, the thermal conductivity will be the gas and liquid phase, and one can use and see the variation of K in the temperature range between the minimum and maximum temperature, and judiciously use an average value. The wall heat flux is one of them, either the wall heat flux or wall temperature is constant. Often it has been observed that the experiments are done with the constant wall heat flux boundary condition, and the wall temperature is measured along the axis, and this is the way by which we can calculate Tb x, as one can see that one will know what is the heat being inputted to the system, at what location one wants to measure the temperature, and the flow rate and the properties of the two fluids will be known. So, one can calculate what is the bulk temperature at a location. Now, this is how it is been what we have described, just that the bulk mean temperature can be measured from heat balance, can be obtained by a heat balance, but it is difficult to measure it. However, recently the technique using laser induced fluorescence, where the particles which are following the flow faithfully, and they are coated by a fluorescent material which is temperature sensitive, which gives temperature sensitive fluorescence. So, the efforts are being made to measure the local temperature in the fluid. Efforts are also made to put the thermocouple inside the channel, which may affect the flow slightly, and then look at the temperature field in the channel and obtain the bulk mean temperature from there. Okay. So, let us look at some of the results. This is a typical temperature profile in a unit cell. So, why you see half of the bubble? Because axisymmetric channel, and this is from a CFD computations, which is done in an axisymmetric channel. The black line shows the boundary of the bubble, the other bubble will be on the bottom half, and you can see the temperature. There is a constant wall heat flux boundary condition. So, the heat is entering from the wall, and the fluid is hot, as you can see from this temperature scale, which vary from 301 to 305.5. So, the temperature is hot. Hot is the yellow color or the red color represents the hot fluid, and then this hot fluid is being brought towards the center. So, the heat is being brought by the fluid using convection, and the mixing of the fluid is happening. temperature of the bubble seems to be very high, but remember that very small heat, very little amount of heat is required to increase the temperature of the bubble. So, this is a typical temperature profile, and this also shows us clearly the presence of internal recirculations in the liquid slugs. Now, this is a typical wall heat flux for T for the constant wall temperature boundary condition. So, you can see that the wall heat flux is high in the liquid slug zone and it is small in this region, because that will be Q wall is equal to K dt over dr at the wall. So, the temperature difference will be small in this region. So, the heat flux is small. Okay. So, then Nusselt numbers, and these are local Nusselt numbers. So, you can see that one find or one obtain very high Nusselt numbers in the film region. So, let me remind you at the outset that Nu that has been defined is equal to H d over K, where we have taken this length scale as channel diameter. However, if one look at the heat transfer is because of the film only. So, the actual length scale that should be used here is delta F, and if one take that into account, this will be very small, because delta F over d is of the order of say 10 to the power minus 2 or smaller. So, the Nusselt numbers are not high in this case. This is just because of the length scale being used here, and the Nusselt numbers in this case is about, one can see from here on the y axis, the Nusselt number is about 10. So, this is significantly high when you compare with liquid only flow in the channel for both the boundary conditions. So, that is all. Now, let us look at a bit about the heat transfer mechanism. So, we have the bubbles and the internal recirculations in the liquid slug, and the heat can find different routes to go from the wall in the liquid which has the high heat carrying capacity. So, the one route is that the heat goes from wall, enters from the wall, and it goes into the bubble film or the film that is surrounding the bubble. Because the heat carrying capacity of this bubble is very small, so it cannot carry much of the heat. So, it waits until the next slug comes in, and then it supplies this heat to this slug. So, that is first route. Now, the second route is that the bubble film, it passes on the heat to the liquid slug. So, and thirdly, that the wall to the recirculating liquid slug zone. So, the heat enters from the slug region, that passes the heat from via this film to the liquid slug directly. So, one need to remember, or the general picture is that because the heat enters in the film, but the bubbles, if it is gas liquid flow, then the bubbles do not carry much of the heat, and this heat is taken over by the liquid slug which comes behind. If it is a gas liquid or if it is a liquid liquid flow, then this heat will be redistributed between the two phases. Okay. So, we will look at, when we develop a heat transfer model, we will look at this correlation further on. So, let us look at some of the correlations that have been presented in the literature for predicting the Nusselt number in Taylor flow regime. So, this Nusselt number is defined as Ne is equal to 1.615, and now you can remember the inverse gadget number, which is REPR, channel diameter by L raised to the power 1 by 3. So, this what they have done is modified the Grigid-Leverque solution, which is for thermally developing flow, and in this solution they have included the effect of bulk viscosity. It is like C.8 equation for single phase turbulent fully developed flow, and then they have introduced the effect of homogeneous void fraction in terms of beta. So, that has been modified to obtain the Nusselt number. Another correlation is similar modification by Grigid. So, they had a simpler modification, that this is the slug Nusselt number, and from that one can just calculate the thermally developing flow. So, basically they said that the heat transfer in the slug region is thermally developing flow, and that can predict the Nusselt number for the Taylor flow. Okay. Kreuzer, they did some experiments. They wanted to do, I mean, most of their work was based around mass transfer in Taylor flow regime, and to develop a correlation for mass transfer, they did a simulation for heat transfer, and from there they looked at the Nusselt number in the slug region or a cavity, which was that they have done a simulation where the cavity in which these are two walls, and these two walls are moving. So, the fluid will eventually develop recirculation inside it. So, they calculated the Nusselt number in these cavities and found this correlation for the slug Nusselt number. Walls et al., they developed another correlation in the slug region, and that was Nusselt number into homogeneous void is equal to homogeneous void fraction into single phase fully developed Nusselt number depending on the boundary condition plus 25 Ls by d raised to the power minus half. So, again the effect of developing length. So, we will stop here. So, in summary, what we have looked at in this lecture is Taylor flow in microchannels, the heat transfer in this flow regime. Before that, we looked at the basics of heat transfer, in particular the definition of Nusselt number, definition of heat transfer coefficient, and definitions of bulk mean temperature. So, by looking at these definitions, we have also seen later on that when we looked at some of the correlations that have been developed for Taylor flow heat transfer, they are based on the developing flow in for liquid only flow in a channel. Okay. So, in the next lecture, we will look at the heat transfer in the Taylor flow regime and a general correlation that can be developed for heat transfer in the Taylor flow regime. Thank you.